Hello folks, good evening. Well, last night we had a look at linear motion and the definitions of various things that went with that. For instance, we had a look at what is distance, what is displacement, speed, velocity, and acceleration. And this is for motion in a particular direction. Okay, so now we're going to look at projectile motion. Alright, so this projectile motion meaning you've got a projectile and you are firing this projectile, or you are kicking it off the ground if it's a football, and so on. Okay, just as I did yesterday, I will pan across to the board so that you can see what's going on. Now, before I start, this particular video will give us an opportunity to look at concepts like gravity, but not in great detail. For gravity, we'll be looking at a particular video, so we'll do a video just for that. Now, I was also toying with the idea of including the equations and the like in projectile motion, and the equations are simple equations, but if you don't know anything about maths, then you might think that they're complex. Okay, so what I've done is I've called this one an introduction to projectile motion, and then in further ones, then I'll do a detailed example of projectile motion. That'll be for those people who are interested in how that works and the maths that goes with it. Okay, otherwise this is just simply an introduction to show people what is projectile motion, how do we know what the components are, and how do we calculate them, how we use projectile motion, and what does gravity have anything to do with it. Okay, so let's start. Okay, so I'll pan across to the screen. There we are, and you can have a look at that. And that's got projectile motion at the top, and we're having there with our little friend from Manchester United kicking the ball, and he's kicked the ball up in a parabolic path, which is what will happen if for any projectile. Okay, whether it's a bullet, or whether it is a missile, or whether it's somebody kicking something off the ball, or playing tennis, you name it. If you hit something, it will follow a parabolic motion, just like you see over here. So the footballer kicks the ball off the ground at a certain angle. So this angle, theta represents this angle over here, and that's the angle at which this footballer kicks the ball off the ground. Now, the footballer starts off with an initial velocity, so the very second that the foot meets the ball creates a velocity, and that velocity then extends and then creates acceleration. So it accelerates up and then and reaches the top over here where velocity becomes zero, because now it's reached its maximum height. So that's its maximum height, and now it is now going to come down. So from there, it's coming down. Now, the important thing about this is it's got a number of components to it. Well, first of all, it's got a horizontal component because the ball is going that way. Okay, so in other words, it's going to be from here and it'll end up over here, so it's obviously got a horizontal component, but it also has a vertical component. Okay, vertical component, first of all, it's going to go up, so there'll be something that fights against it going up, and that is gravity. So it's going up, and then it also has to come down, and therefore its gravity causes that as well. So now let's see what are the implications for gravity with this. Now, so flat earth people say that gravity isn't a thing, and yet we're able to use gravity in order to be able to make very, very precise predictions for this projectile motion. For instance, if we know the velocity at which this footballer kicks the ball, we can predict not only how high that ball will go, but we can predict how far it will go as well. So a good footballer will know pretty well how to kick a ball to get a distance that he or she is after, because they are experienced in knowing what angle to kick the ball off the ground and how much force to give it. Okay, now similarly, a golfer will have a particular golf club shaped in a particular way that will take the golf ball to a certain height, and given it that height and also the swing, the golfer knows how much to hit the ball, and it'll go at a certain height because of the shape of the golf club, and then as a result of that come back and then end up in a predetermined distance. So not only will the golfer have a pretty good idea how high the ball is going to go, but the good golfer will know pretty much where the ball is also going to land. Okay, similar thing with a missile. So again, the ship over here has to hit a target over here, and the ship then has to can see what the range is. This can tell what the range is, and then once they've got that could be via radar, so they know what the range is, and then they'll be able to determine what angle to aim the gun in order to achieve this range. Okay, so they know where the other ship is, they know where that target is from the range, and then they're going to have to adjust this angle here to be able to tell what angle to fire it at so that it will hit that target. Now all that depends on gravity. Okay, now not just dropity or things are falling down, or buoyancy and density, okay, which are just total flat earth nonsense. This figure over here actually matters, this 9.81 meters per second squared. So when you have a look at this graphic that I've got over here, I've got this little red ball and this large black one, and they are both going to fall and hit the ground at the same time. Now, provided that, of course, they both are going to be able to overcome friction from the air, they'll hit the floor at the same time. Why do they hit the floor at the same time if they are different mass? That is because everything accelerates to the ground at the same rate, 9.8 meters per second. Okay, this is the acceleration, and acceleration is little g. So little g, 9.81. Okay, so they fall at the same rate, and yet they weigh differently. They have different force, because force equals mass times acceleration. So because A and G are the same, force is equal to mg. Okay, in fact, often things are talked about weight in newtons, because newtons means the mass of the object multiplied by 9.81, which is the gravitational pull. Okay, so who says gravity doesn't have a force? Well, gravity with mass has a force. Okay, so gravity, which is acceleration and gravity are the same. Mass times acceleration gives you a force. Mass times gravity gives you a force. Okay, so mass is an integral part of the force that's created by gravity. Okay, so this is what's meant by gravity having a force, being a force. Gravity is a force if it's combined with mass. It doesn't make any kind of sense to talk about gravity without also including mass. Now, okay, so let's move on. So again, these two objects will fall at the same rate because gravity is the same for both of them. Okay, what have we got over here? Over here, let's say this is Earth, over here. Okay, and we've got our little friend from Manchester United, who can kick a ball pretty good, as most of those people from Manchester United can. Now, so our little friend here kicks the ball, and it lands over here somewhere on the Earth. So let's say just at the minute, this isn't to scale. Kicks the ball and has another crack at it. So this is the black one, has a crack at it and says doesn't quite make it where he wants it to go. Has another crack at it, and then it lands even further along. And again, then shoots again and says no, that's not good enough, and hits it so hard that in fact it doesn't hit the ground again. It keeps going right around like this, keeps going right around, and then keeps going indefinitely. So he was so strong, he managed to hit the ball with such a velocity that overcoming the gravitational field of Earth. Okay, so that would require him to have a speed of 40,000 kilometers per hour in order to reach the escape velocity, or 11 kilometers per second to reach the escape velocity for Earth. Now clearly that's not a problem for a missile or a rocket. Okay, so they would have sufficient fuel and oxidizer on board to be able to produce lift, and that lift would be able to overcome Earth's gravitational field. They would be able to overcome the 40,000 kilometers per hour that they need, or 11 kilometers per second, in order for them to put them in orbit, and then from there they can cut the engines and it will remain in orbit as long as it's moving. Now you're asking yourself, why does it keep moving then? Well, it's obeying Newton's first law, because there's nothing there to stop it from moving. So an object will remain in motion until something stops it, okay, or until something affects it or changes its direction. So it will move in the same direction. So the satellite, once it gets up there, or the rocket, once it gets up there, there's nothing there. There's here to stop it. There's no friction to worry about. So this will just keep moving in perpetuity in that orbit. Okay. Now let's have a look across over here. So here's an example of two different orbits. For instance, this is something that we do quite a bit. We've got two types of orbits here. This one in red is a polar orbit, and it goes north to south approximately 5 degrees, and it will keep going north to south. So the rocket that starts somewhere over here in India goes to the South Pole, actually very close to Australia, actually pretty much over New Zealand. So if you picture that, the other New Zealand over there somewhere, Australia on the other side, then it will pretty much go through New Zealand like this. So it'll go down south and then keep going around like this, and as it's going around like this, so it's got enough speed to get it into orbit. So it goes into orbit, goes around, and as it keeps going around like this, just goes on and on and on like this, the Earth is spinning underneath it. And as the Earth spins underneath it, this is spinning around this way, this is orbiting around this way, it's able to take a picture of the Earth, and depending on where it is, if it's high enough, it'll get the Earth every 12 hours. If it's otherwise, depending on where you want it, it can take a picture of the Earth, of all of the Earth. In other words, cover the entire Earth in 24 hours. That depends on the location of the satellite. Now that's a very important type of satellite. These are called low Earth orbit observation satellites. They follow the sun. Obviously you want to follow the sun because you want to see what's happening in the sunlight. They'll follow the sun, and and be able to take pictures of the Earth, many thousands of pictures of the Earth, in order to cover the entire Earth in the 12 or the 24 hours. Also, then, this one over here, this blue one, that will be the geostationary orbit, and that goes in the same direction that the Earth is going around. So it will, again, because it's going at the same speed of the Earth, then it's going to appear to stay in the same place all the time. And of course you need that, because your house might be somewhere over there and you've got a TV dish on your house roof, and it's pointing, so us down here, pointing towards the equator, right up there at 36,000 kilometers it is, pointing right up there, and we want to keep it there. So I've had mine about 12 years on the roof, haven't moved it at all, and it's been pointing at the same satellite for a very long time, for all those 12 years, and I haven't touched it. So thankfully for that satellite, it's stayed in the same place all this time. So as the Earth is moving around, that satellite is keeping pace with it, so that this is always in the same direction, pointing away from my house, so I don't have to adjust the dish that's on my roof. I hope, if you are a flat Earth person, you just heard that what I've just said, and that's kind of rings a bell with you, because no doubt there are plenty of satellite dishes in America and plenty of satellite dishes in England. This is where the majority of flat Earth people come from. So both those places have plenty of satellite dishes. You need to have a look at it and see which way they're pointing, and you'll find that all of them will be pointing in roughly the same direction from where you live. So they will be pointing towards the equator. Okay. All right. So now there's nothing really else I want to go through with this. So the next time I'm going to go through circular motion, and we'll discuss the movement of the Earth in more detail, and we'll also talk more detail about the satellites and rockets and how they get up there. Okay, so if you are interested in learning much more about projectile motion, and you want to be able to learn how to do these calculations, I'm more than happy to put a video up that's going to do that. In any case, I'm teaching freshmen this year, so I'm going to have to do this anyway. So probably at some stage around March or thereabouts, I will have a video that's aimed at university students, and of course I have to cover that in detail. All right, but for now, this is an introduction into what projectile motion is. If there's any takeaway from that for you, and that is the importance of gravity, the importance of us knowing that the gravity is 9.8 meters per second squared. Okay, and not only that we know that, but we're able to make extremely accurate predictions based on that. Okay, so that Newton's equations that go along with this make beautiful predictability, and goes to show again how immensely brilliant Newton was in his day, and even if you compared him to anybody who lives today, Newton would still be far ahead of anybody that I can think of. Okay, all right. So if you are interested in more videos, then please press the buttons down there. You know, subscribe and the bell and the like button if you like the video, and then I'll be feeling like doing more of them. Okay. All right. So what's coming up? Circular motion. That'll give us a chance to look at how the Earth is spinning, and we'll look at some of the evidence, okay, that shows why the Earth is spinning. So I hear this nonsense because one day somebody famous, perhaps Einstein, said there's no way to tell whether it's the Earth that's moving or the planets that's moving around us. So is the sun moving around us, or are we moving around the sun? And basically said there's no calculation that you can do to tell which one is which. Okay, now this is really a philosophical question, and the person who said that, like Einstein, wouldn't actually believe that. Okay, it's possible that the sun is going around the Earth, right? There's not a chance that Einstein would think that, would have thought that, or that was even possible. Okay, the idea that you're saying that you can't tell which one is the one that's moving is really just a philosophical question. Okay, and because Einstein would have been talking about relativity of motion. Okay, so it's a bit like if you didn't know you were sitting at lights, you couldn't. One person was moving. You know, sometimes you're sitting at lights and another person next to you starts moving forward. You almost get a shock thinking that you're moving backwards. Okay, all right. I'm sure that's happened to everybody. And in fact, it's not. It's you quite still. You know, perhaps daydreaming, and the person in front of you starts moving forward. It feels like you moving backwards. Okay, all right. I'm sure everybody's come across that before. Okay, so Einstein would have been talking about relativity at the time, and talking about this philosophical question. So if you are one of those people who keep repeating that nonsense, stop it. Okay. All right. Okay. Let's catch up in the next video. Cheers.